So, as we have seen, the glyceraldehyde OH having right side, its mirror image will have a OH left side, and it will be the enantiomer of the other compound. Like that, there are so many examples. Like for example, if you have a 2-chlorobutane, this is called systematically 2-chlorobutane. It has a chiral center at the second carbon. You can write this molecule in the Fischer model like this. So, one methyl group on the top, this whole thing you can club and write C2H5, and one of the chlorine let us write on the right side and the left side. This is A, its mirror image will be the B. So, if question comes, write like 2-chlorobutane, write the two isomers of optical isomers of this compound. Now, A and B is written, but only polarimeter will decide which is dextro, which is levo. We can say the important group right side, therefore, this is capital D. Okay, D and L can be decided by me only because it is related to the structure. Structure designation is right side, left side. When I write the molecule in the Fischer model, the norm is molecule should be written in the vertically stand-up model. That is the lower preference given carbon. You start numbering from here according IUPAC system. So, one goes to the top, or more oxidized, in fact, more oxidized from side only we give the numbering. Lactic acid, COOH is more oxidized. So, I will give the number 1. So, always generally number 1 will go on to the top and the least preferable number comes down. When this is not important, you can club and write C2H5 or ETME symbols you can write. The idea is this carbon with 4 groups should be shown clearly, of which the important group, that is horizontal group right side, capital D is assigned. Property, is it plus or minus? It is a question mark. We can't decide this, only polarimeter. What value also you cannot guess. Oh, you have 7 carbon, therefore this is the value. You can't. So, value and the plus or minus you can't. Only in the carbohydrates the plus value based on the D we are able to, otherwise no. So, this compound, if it is given, write its isomer, means these two. One of the isomer is dextro, capital D, value we can't say, but one is dextro, one is levo. These two are called a set of enantiomers. But if a next example, let us go. This is a carbohydrate again, having the 4 carbons it is, and 3 carbons have the OHs now. So, systematically call this compound as a 2,3,4 trihydroxybutanol. It has 2 chiral centers. This is not chiral because 2 hydrogens are there. So, here 2 chiral centers are there. There is one rule called Van 't Hoff rule. According to this compound, the number of optical isomers come from this one is 2 to the power of n. So, n is the number of chiral carbons. So, therefore, 2 to the power of 2, that is 2 into 2, that is 4 isomers are coming. 4 isomers are coming. Out of these 4 isomers, 2 pairs are going to get. What are these pairs? Means original and its mirror image, another original and its mirror image. So, 2 pairs of enantiomers are coming. 4 compounds means 2 pairs of enantiomers coming. How do you write these enantiomers? Means as a default, I write first the 2 chiral carbons, lower one is CH2OH, this is non-chiral one you can club, this is non-chiral you can club. Only chiral carbons 2 OHs right side I write. Now, this is the one which decides whether it is capital D or not. When you write molecule in the Fischer model, from the bottom, that is the first chiral carbon of the from the bottom, if the important group is right side, we call this compound as a capital D. In the carbohydrate, it is so happened, it is a dextro compound, plus or dextro compound. So, it is a D with this compound, it is called 2 OHs same side, its mirror image is possible now, 2 OHs same side compound is called erythrose. We have a first set one name, second set another name. Instead of same name with the 4 compounds, D-erythrose I call. A book also says that remember that 2 OHs same side, just like a capital E has got hooks on the same side. So, erythrose is given for these 2 compounds. One is D, as I said, in the carbohydrates it is known. So, it is L compound, therefore, it is a minus erythrose. D erythrose, L erythrose. And another set, these 2 are the one set of the enantiomers. Let us say the 1 and 2. 1 and 2 are the a set of enantiomers. You took at another set of enantiomers. The OH, let us keep it as a default. First one as a dextro compound. Once again, it is dextro compound. Rest you CHO. The OH now you write opposite side. So, this is the compound 3. Its mirror image is a compound 4 is a mirror image of the 3. So, it is enantiomer for the 4th compound. Is the enantiomer of 3rd compound. So, this is having a OH once again D and the other one is L, and it so happened it is coincided that this is D triose. As I said, E is used for the 2 OHs same side, just like E letter, one this side, one that side. So, just like a T letter we are using triose. This is D triose, the other one is L triose. So, there are 4 compounds, D erythrose one set, triose another set. There are 2 sets of enantiomers are there. So, I write like this. This is called interrelationship. Interrelationship. So, 1 and 2 and similarly 3 and 4. These are called enantiomers. Enantiomers means we have already defined. This is a set of compounds having exactly mirror image relationship. But if I try to put one over the other one, that is called superimposability, not possible. So, 1, 2 is a set of enantiomer, 3, 4 is also a set of enantiomers. But if I take one compound from this pair, compare with one of the compound with other pair, they are not enantiomers, they are one from this, they are called, still they are optical isomers. 1, 2, 3 are optical isomers with this formula. So, therefore, 1 and 3 are still optical isomers, but not enantiomers. So, we have one litigation here. 1 and 3 are optical isomers, but not enantiomers. Then what will be they mean? Say we have another term is called 1 versus 3 is said to be a diastereomer. Diastereomer. Now, here in this particular case, diastereomers are explained. If you carefully observe the 1 and 3, see the lower part chiral carbon is ditto, upper part is mirror image. That means out of the available n number of chiral carbons, a part of the chiral carbons are same, remaining part of the chiral carbons are mirror image. That means a part is a ditto compound, a part is mirror image. It is not totally same means same compound called homomer in fact. Otherwise, if it is totally mirror image, it is enantiomer. So, it is having the 2 qualities, half homomer type, half or not, may not be exactly half. A part is mirror image, a part is ditto. In such a case, we are calling diastereomers. However, we have a reclassification or the recognition of this exact what exactly the meaning of diastereomer we will take later. But 1 and 3, similarly 1 and 4, 2 and 3, 2 and 4. So, all these 4 sets are also called diastereomers. Either the lower part or upper part happens to be a mirror image and the other part will become the same. So, therefore, total 6 sets, because 4 compounds are there, 6 sets you can make. Out of that 6 sets, 2 sets are enantiomers, remaining 4 sets happens to be diastereomers. And as the case, this is carbohydrate, therefore, I am able to guess whether the given compound immediately capital D or not. Consequently, whether it is D or L, But as I said, that by seeing the structure, no one can guess whether it is dextro or levo. Only the right side important group, that too when you have so many chiral carbons, let it be the upper carbons whichever the side, but the lowermost chiral carbon horizontal group important right side means we designate with the capital D, and this capital D happens to be this DL nomenclature is outdated now, because it is giving only a part of information, leaving the upper chiral carbons information. So therefore it has become outdated. In this place we have an absolute nomenclature called RS nomenclature. We will see that later. Like this number of chiral carbons, we can calculate what type of chiral carbons are there, how many isomers are getting. But let us have another type of the example. Now we will take another type of the specific example, that a COOH group and a CHOH and another CHOH and a COOH. This is systematically called 2,3-dihydroxy butane dioic acid. You can call it as a 2,3-dihydroxy butane dioic acid. You need not to say 1,4. Dioic acids will be at the end only. So therefore you can simply say dioic acid, not necessary to say 1,4-dioic acid. So it is a butane dioic acid with 2,3-dihydroxy. There are two chiral centers are there. So what is the number of isomers? We guess is 4 isomers, because 2 to the power of 2, 4 isomers we are going to get. But our calculation goes wrong here. Why it goes wrong means, first let us expect what happens, we will see later. So according to our calculation, so this is the 2 OHs same side, that is called erythro type of compound. Its mirror image is another erythro compound. So this compound has a common name called a tartaric acid. Tartaric acid is the reason to have a sour nature to the tamarind. So the tartaric acid is there in the tamarind. So this is another tartaric acid, so which is having a same side. So let us use the old nomenclature based on that erythros. So let us call this as a small d. Again the OH, you can guess, you cannot guess D, but capital D you can guess, but small d just is only a guessing. So small d erythros, erythro tartaric acid. This is small l erythro. I am not saying erythros. Erythro means erythrotype. Okay, I am using symbolically. So L erythro tartaric acid. The other two I call thiotartaric acid. One OH right, one OH left. So let me first guess and write the structures. D-thio. D-thiotartaric acid, and its mirror image will be the OH, COOH, and other groups are hydrogens. So L-thio tartaric acid. So this is what I guessed. Then where going the wrong means, if you carefully observe the compound 1, compound 1 as a line that is going to cut this compound into two halves, right? That means it is a compound which cuts into two halves. As I said, apple with symmetrical parts, optical activity will be 0. So this optical activity will be because it has a plane of symmetry. The other way also can be studied. This is a chiral carbon, right? So this chiral carbon, imagine that it is producing the plus 35, right? This chiral carbon is a mirror image of the first one, see, exactly mirror image. So it produces minus 35, right? So get cancelled, that's why 0 is coming. So either way you can define, because the molecule has a planarity, that's why whole molecule is symmetric, that's why. But at this level it is unsymmetric. See, if you cut here, it is unsymmetric. At this carbon you can't cut the compound into two halves. Therefore, there is a chiral carbon, it is producing some value which is exactly the mirror image of this carbon. So, therefore, it produces minus 35. Net adding you will get the 0. That is why this compound optical activity is 0. When it is 0, you cannot have dextro. Dextro means right side or positive side. 0 cannot be plus, isn't it? That is why D is removed. So, when you have a 0, its mirror image, that is dextro is not there, levo cannot be there, isn't it? Both will be nothing but the 0 compound. It is also proved that as such the compound cannot be superimposable. If I bring like this and keep it, the OHs are right side. But you can do one thing, rotate this molecule on plane, it is allowed. COOH comes here, COH goes there. The two OHs comes this side. Then you put it over this compound. That means my two photographs, one front side photograph, one side way, two photographs are given. And are they superimposable? Means you should not try as such, isn't it? You imagine that what will be the front side photograph of mine, and then try to superimpose and see, verify whether it is same person or not. Like that here also, as such if you superimpose it is not possible. But if you rotate, our best way is prepare a model of this compound by going back to the three-dimensional model, prepare a model and prepare a model. This model exactly sits, just like we have a chair, plastic chairs, put the chair on the other one, it sets. If you press, imagine the first chair is not there, second chair exactly sets in the place where the first chair was there. Like that this molecule sets in the place where this was there. So, that is these two are proved to be identical compounds. Let us put this symbol, identical compounds, and these two are said to be homomers therefore. Which two are homomers? 1 and 2 are homomers. 1 and 2 are homomers. They are nothing but the same. This compound is nothing but. So, therefore, in this particular case where optical activity is 0 and its specific name I am giving, instead of D I am nullifying because it is not positive, negative. Even deritro also I am removing. I am using a specific word called meso. Meso stands for the neutral or 0. So, therefore, to reflect this particular idea, I am calling the compound 1 as a meso-tartaric acid. What about 2? 2 won't be there at all. I just cancel it because it is nothing but the repetition. So, 2 won't exist at all. There is only compound 1 is there, 2 won't exist. However, 3 and 4 exists because this is a first half is not a mirror image of the second half. So, therefore, both the carbons will show some plus 35, this also will have some value, but not exactly cancel. So, one will have a dextro and the other one is mirror image. So, therefore, it will have its mirror image. So, these two compounds will be there, but in this case also I am dropping this trio word. In the erythro I dropped, therefore, trio is dropped. So, in this first compound is called meso-tartaric acid, third compound is called just D-tartaric acid. D-tartaric acid, not using trio, but make it very clear, D-tartaric acid means trio only, and L, this is also called L-tartaric acid. So, there are only 3 tartaric acid, though it has 2 chiral centers. Total isomers possible for the tartaric acid, not the 4, it is only 3. One is meso-tartaric acid where OHs both are either right side or left side, nothing but same. Another set, so one set of tartaric acid, enantiomeric set 1, one non-enantiomeric compound. This is a one single compound. If relationship, interrelationship it is asked, 1 versus 3 or 1 versus 4 is diastereomers. What about 2 versus 3? 2 and 1 is nothing but same. Therefore, whether you take 1 or 2 is nothing but same. So, 1 and 3 pair is nothing but 2 and 3 in fact. So, therefore, 1 3 1 4 or 2 3 2 4 are nothing but the diastereomers. 3 4. So, now here 1 and 2 is called homomers, is nothing but the homomers. 1 and 3, 1 and 4 is diastereomers. Whereas 3 and 4 is enantiomers. So here you got getting one more word, that is homomer. Homomer means nothing but same compound, it is nothing but the same. When you are getting this type of the homomer means compounds may be written in different pattern. Ask that whether these two compounds are not same or this different one, then you have to prepare better its three-dimensional structure, you visualize it and then see that it is superimposable or not. Any two compounds which are exactly superimposable are said to be identical in all respects. Such two compounds are called homomers. So in this case 1 and 2 appears like a mirror images, but that is not correct. Correct is they are nothing but the same compound, therefore we call homomers. And 3, 4 is an as usual enantiomer. One from this one from that one, if you take, that is a diastereomer. Either one or even take 2, 2, 3, 2, 4 is also nothing but the diastereomer. Like this we have huge number of examples, like a phenyl with a CHOH. This is a, if nothing is there this side that side, it is called a ethylene glycol, diphenyl, 1,2-diphenyl ethylene glycol. Or you can take a 1,2-dichlorobutane or dibromobutane. Both the ends groups should be identical and this and this will be identical. There is a line that cuts exactly half. In such cases we are getting this type of the meso compound, and expected 4 isomers are not getting, because one isomer gone, repetition. So therefore we are getting the less number of the compound. So therefore we have a identification or calculation of the optical isomers versus a given compound, checking how many chiral carbons are there. Based on that we can calculate how many the optical isomers are possible. That we can do now. So we are going to calculate the total number of optical isomers when the structure of the compound is given, or by observing the number of chiral carbons present in the given compound. So we have divided the compounds into two types. One is non-divisible molecule. That means the molecule, if you cut anywhere, you cannot get two exact pieces, like for example A, B, C, D. These are all the examples where you cannot cut the molecule into two halves. Whereas the other section is divisible molecule. That means if you can cut at one place, you will get two halves exactly. So therefore such a molecules we can call it as a divisible molecules. So the working pattern will be different. For the non-divisible molecules, A stands for the active isomers. That means compounds which show optical isomerism, they are called active isomers. The compounds which have the chiral carbons but internal the compensation and all that, this M stands for the meso type of the compounds. P for the pairs, how many pairs we are getting. T for the total isomers. So let us have some abbreviation and then we are following. So the A, that is total active members, will be 2 to the power of n, where n is the number of chiral carbons here. N is equals to number of the carbons with 4 different groups are chiral carbons. If the chiral carbon 1 is there, we are going to get 2 active members. One is dextro, one is levo. An example A here, 2-chlorobutane, that is secondary butyl chloride, will have the 2 isomers. So similarly, if the n is, that is 2 isomers will be there. Meso compounds always if divisible, non-divisible compounds, for all non-divisible meso compounds will be 0. Pairs will be active members divided by 2, always A by 2, this is common to all. Total will be the generally meso compounds and active members together is the total, but here meso happens to be 0, therefore only A will be the representing, therefore what all A here is repeated here. If one chiral center 2 to the power of 1, that is 2 isomers, 2 chiral center 2 to the power of 2, 2 into 2 4, 3 chiral center 2 into the power of 3, that is 2 into 2 into 2, that is 8. and one more 4 chiral center 16, 5 chiral center 32, 6 chiral center 64. Every time it will be double. All meso compounds will be 0. A by 2, that is pairs will be always number of active members by 2. That is if 2 are there, you are getting 1. If 4 compounds are there, pairs will be 2. 2 compounds 1, 8 compounds 4. Like that, the number of the pairs will be half of the active member. 32 half, 64 half 32. Like that, the active members, that is pairs, will be always half. And in this case, meso compounds are 0. Therefore, what are A? We are nothing but getting the total members. Coming to the second part, that is divisible into 2 halves, like tartaric acid. This is the tartaric acid. At this center, if I cut, the same parts you are getting. So, therefore, in this case, we are going to have a slight modification in the that is formula we are using. For active members, we used previously 2 to the power of n. Here n minus 1, some compounds are meso compounds coming. Therefore, this A will be always less than this A. So, what is that less means? Minus 1 factor we are using, n minus 1, 2 to the power of n minus 1. Let us see here, 2 chiral centers are there. Actually 2 to the power of 2 means 4 isomers you will get, but only 2 are getting, and 1 meso compound n by 2, that is 2 by 2, 1, 1 minus 1, 0, 2 to the power of 0 means 1. So, 1 meso compound, its companion will not be there. The another set is active, meso tartaric acid, D tartaric acid, L tartaric acid. This is in the case of G, example G is tartaric acid. In the case of tartaric acid, 1 D, 1 L, 1 meso. So, total 3 compound, 2 active members, 1 meso compound. There are some questions. If this formula is given, how many active isomers you are getting? Actually, expected 2 to the power of 2, 4. 1 compound is a repetition. So, therefore, 1 meso, 2 active. So, active members alone, if it is asked 2. Total isomers, how many means? 2 plus 1, total is 3. So, 1 is pair. 1 pair means 1 dextro, 1 levo. So, pairs separately we have a column here. And similarly, when 4 chiral centers are there, 2 identical ends, see, this is methyl. If this happens to be ethyl, it goes to be a non-divisible type. Both the ends and the groups all will be chlorine. This side chlorine, that side bromine means not possible. Chlorine, chlorine, bromine, bromine is allowed. That means if I cut here, 2 halves identical, then only it will be divisible molecule. Okay, a divisible molecule having even number, the 2 and 4 is even number, 3 and 5 comes odd number. So, under the divisible molecules, we have another factor, even number of chiral carbons and odd number of chiral carbons. The 2, 4, 6, 8 comes under this category, and odd number like 3 and 5 happens to be another type of this section. So, in the first section, even number of carbons, tartaric acid and glutaric acid type and so on, we have a divisibility here. So, we have to calculate, for example, 4 chiral centers are there, 2 to the power of 4 minus 1, 3. 2 to the power of 3 means 8 active members will be there. Meso compounds are 2 to the power of, that is, this is 4, chiral carbons 4, 4 by 2, 2, 2 minus 1, 1, 2 to the power of 1 means it is 2 isom. So, 2 meso compounds, 8 active members. So, 8 active members means 4 pairs will be there, 8 plus 2 total is 10. Like that, if 6 chiral centers are there, so 6 minus 1, 5, 5, 2 to the power of 5 means 32, and 6 by 2, this is always even only, 6 by 2, 3, 3 minus 1, 2, 2 to the power of 2 means 4. So, 4 meso compound, 32 active members, total will be the 36, however 32 half 16 pairs you are going to get. Like that, the calculation, only thing is first given compound, first whether you see that whether it is cut into 2 halves or not. If it is not cut into 2 halves, comes under this section, non-divisible, just simple formula 2 to the power of n, meso will be 0, A by 2 is, these 2 you need not to remember, always pairs will be total by 2, and total will be active plus meso, meso is 0, only active will become the total. In this case, we have a small difference. Active member is 2 to the power of n minus 1, and here active is N minus 1 minus meso compound. This working is slightly much more difficulty now. First you see the meso compounds. N minus 1 by 2 is the meso compounds. N minus 1 divided by 2 is the meso compound. That meso you have to remove from the active members. So then only real active members will come. So like this, for example, chiral carbons are 3, for example. First calculate the meso compounds. Meso compounds are 3 minus 1, 2, 2 by 2 is 1, 1, 2 to the power of 1 means 2. 2 meso compounds will come for these compounds. 2 meso compounds will come. And the 2 active members. For example, if this compound is worked out, you will get the like this. All the OHs same side is one meso compound. Its mirror image happens to be same, nothing but same. This A and B is nothing but same. Its mirror image will be there, but this won't be there at all. And there is another compound, one OH this side, 2 OH that side, also is a meso compound. This is also another set of meso. You too get its mirror image, but it is nothing but the repetition. So A, B won't be missing, C, D will be missing. So out of A, B, C, D, only A one compound, C one compound. Its mirror images are duplicates or same compound. But whereas if the compound is 2 one side, 1 one side, this compound is an optically active compound. It, and let us say this is A, B, C, D, E, and its mirror image is F, totally new compound. Okay, and similarly the out of this so 2 OHs, the 2 ends are COOH, isn't it? Divisible with then you have a 2 active members and 2 meso compounds. Total is 4 therefore. A, B, D won't be there. A, B, C are the meso compounds. E and F are the active members. So 2 active members and the 2. So for this one, 2 active members. For this particular case, 2 active members, 2 meso. Total is 4 compounds. That is A, C, E, F are the 4 compounds net. So therefore, first calculate the meso compounds. 2 minus 1, that is 1. 1 by 2, that is 3, 3 minus 1, 2. 2 by 2, 1. So that is 2 to the power of 1 means 2. 2 active meso compounds, 2 active compounds. Total is 4 therefore. Like that example J is 3. Trihydroxy, that is glutaric acid actually. 2, 3, 4, 5. 2, 3, 4. Trihydroxyglutaric acid will have the 2 active members and the 2 meso compounds. And coming to the next last member, this is also a repetition of this. If 5 chiral centers are there, but at this carbon, in the center of the carbon, if you put a line, they are identical, therefore it is divisible, but odd number is there, so come under the odd number category. So apply this, first calculate the meso compounds, applying n minus 1 by 2. That meso compounds you remove from n minus 1, then you will get the active members. So like this, first see the compound whether it is divisible into 2 halves or not. Then if it is divisible, even number of chiral carbons or odd number of chiral carbons. So applying this, one can easily calculate in a given compound whether it is belongs to this category or that. So 4 things you can calculate. One is total active members, total meso compounds, and pairs, always active members, half will be the pairs, and total will be the meso and active, together will be the total. So that is what calculation of the optical isomers.